Hello. Let's turn this off. Right, so today I'm going to cover benzene, and it's the structure of benzene I really want to get to grips with. The story starts with the molecular formula of benzene, which was for a long time known about, and it was C6H6. Benzene being a liquid, an oily liquid, colorless oily liquid, could be burnt, etc., and could measure the amount of carbon dioxide and water vapor given off, and from that you could calculate the ratios of carbons to hydrogens and work out the molecular formula C6H6. But they didn't know the structure, and there was a German chemist called Kekulé. Kekulé was the first one who said that I think I know what the structure is, and if I draw it on my overhead projector, he thought, wrongly as it turns out, but what he thought was that the structure was this. Now, if we look at that simply gives us 6 carbons in a ring structure, and off the carbons there is a hydrogen. And that gives C6H6. But at that time they also knew that carbon has a valency of 4, hydrogen has a valency of 1, and therefore to satisfy the valency, Kekulé suggested that there's a double bond there, and then single bond, double bond, single bond, double bond. And in that way, that is the Kekulé structure, and in that way the valencies were satisfied. And for a long time they thought that was the molecule called benzene. But more recently, when we have more spectroscopic methods and we've got more chemistry, then this structure came to be questioned by chemists. And let's have a look at some evidence of what evidence was there that this structure that Kekulé proposed was indeed wrong. Well, firstly, you should know from your alkenes work, if I just turn this off for a bit, you should know from your alkenes work that alkenes are very reactive. They react with bromine, you shake them with bromine water, decolorizes the bromine water. You can do similar experiments with chlorine water, shake it with chlorine water, and the chlorine molecules or the bromine molecules, well, they react rapidly with double bonds, and the double bonds open up and they add bromine across them, or they add chlorine across them, or you can have other molecules like hydrogen chloride or hydrogen bromide, etc. But we've learned already from year 12 work that alkenes are very reactive. So if you have that structure, the Kekulé structure with 3 double bonds, you'd expect that to be reactive. You'd expect the same reaction at 3 sites that we're already familiar with when we're dealing with reactions of ethene and halogens. But what we find is that doesn't happen. What we find is that if we have this structure, and let me show you on the overhead projector, then with, for example, bromine, we don't get the reaction we expect. Instead, we might get something like this. No, let me just redraw that. I'm sorry. So if you look at that, what we end up with is we end up with a monosubstituted benzene. That is, one of the hydrogens has been replaced by bromine. It's not the addition reaction that we thought we would get. And therefore that really doesn't tie in with the structure being Kekulé structure. Now, I am going to use the phrase cyclic triene. That to me is cyclic and a triene for 3 double bonds. Kekulé structure is called the cyclic triene structure, or as I call it, the theoretical cyclic triene structure, because we know now it's not the real structure. So what else? What other information, what other evidence counts against Kekulé structure? Well, we can also look at enthalpies of hydrogenation. Now the argument here goes as follows, that if we take this structure, cyclohexene being C6H10 with hydrogen, would make cyclohexane C6H12. And when we do that reaction, we find that the enthalpy of hydrogenation, the enthalpy of hydrogenation is in fact minus 120 kilojoules per mole. Now, if the enthalpy is 120 kilojoules per mole for hydrogenating a double bond, then if benzene were indeed to be the theoretical cyclic triene structure there, we would expect, when we hydrogenated it, we'd expect 3 lots of 120 kilojoules to be given out per mole of benzene being hydrogenated. So we'd expect a minus 360 kilojoules per mole reaction if we'd expect that to react with 3 moles of hydrogen gas. But what we find is we don't get 3 moles of hydrogen gas. We get, when we do it, real benzene. When hydrogenated, has a delta H of only minus 208 kilojoules per mole. Now, this argument is difficult to see. I mean, clearly, you can say the structure is not a cyclic triene, but you can get a lot more out of this experiment, evidence too about hydrogenation energies, if we plot it on an energy level diagram. So on an energy level diagram, where we have the energy here, and we end up with, in both cases, we're going to end up with cyclohexane there. If we have the cyclic triene structure, that's a Kekulé structure, then we would expect that energy gap to be minus 360 kilojoules per mole. But what we actually get is an energy change that is, I'm going to put a circle in there and label that real benzene, whereas that one is just the cyclic triene structure. And you can see there, not only that the values are different, minus 208 kilojoules per mole, not only that the values are different, but you can see that if this is a smaller value, then the real benzene is, in terms of energy, more stable. Now, it's one of the great things of chemistry is talking about stabilities. And when things are more stable, they're lower in energy. It's a bit like if I have a pen on a table, gravitational potential energy is higher, and it's more stable if I knock it off and it falls on the floor. It's more stable on the floor, it's less stable on the table. And similarly with energy level diagrams, as you come lower and lower, then the chemical is more stable. And you can see from the diagram, I'll put it again in a minute, but the diagram will show that the real benzene is more stable. And even more than that, we can even calculate just how much extra stability it has compared to the cyclic triene structure. So watch. This gap here, that gap, is the difference between the two values, and the difference between the two values is minus 152 kilojoules per mole. Now that extra stability of benzene, the extra stability of benzene there is known as resonance energy. I'll use that term later and talk about it a bit more, but the extra stability is this extra stability is more stable by 150 kilojoules per mole than we would expect. And that's really significant. That we're going to use later. And that's really the crux of the matter. That's why it doesn't react. If it were a cyclic triene up there, unstable, it will react much more quickly. But this is more stable. Its energy is lower, more stable, doesn't want to react. And that ties in with our non-reaction of halogens that we've already talked about. And now this is extra evidence against the idea of it being a cyclic triene structure. So what is the structure? So what is real benzene structure? Okay, well, I'm going to try and tackle that now. You know that carbon has 4 electrons in its outermost level. So each of these carbons, if I start by drawing it as a hexagon, each of the carbons using 1 electron each will give us a sigma bond between them all, where we use 1 electron for each of these covalent bonds, another electron for the other covalent bond. So I suppose I may have said 1 earlier, I mean 2. Each carbon uses 2 electrons to make that hexagonal structure, and they're what we pi bonds. They're direct overlap of orbitals. And coming off each carbon, again, we've got more pi bonds, again, direct overlap of orbitals. and these are hydrogens, the s orbital of the hydrogen overlapping with the orbitals from the carbons will involve one more electron. So with that structure, each carbon has used 3 electrons. So each carbon's got 1 electron left over. And that electron left over is a p electron. And the shape of p orbitals is like that. It's dumbbell shape. Now, if you think of all these carbons and hydrogens in one plane, I want you to think about the p orbitals perpendicular to that plane. So if the carbon and hydrogen are in the plane of the board, these lobes are sticking up above the plane of the board and below the plane of the board. And if I draw them all in, then there are 6 electrons that are occupying these p orbitals. Now, this is not to scale. I'm simply trying to show the arrangement. There are lobes above and lobes below. Now, had I drawn it to scale, these lobes here would have overlapped. And you get overlapping of lobes there, like that, above the plane. But then also, if I can get my red pen to work, you can get overlap of the bottom lobes, like that. So that you can see that you've got the atoms, the carbons and hydrogens in the plane of the board. You've got the blue overlaps above the plane of the board, and you've got the red overlaps below the plane of the board. And it's almost like a sandwich where you've got the electrons above and then the atoms and the electrons below. And that is real benzene. What about these 6 electrons? Well, the 6 electrons are delocalized. They're free to move around within the molecule. They can jump from carbon to carbon and they can move around pretty freely. And that's why we draw the structure of benzene like that. And we put a ring. The ring represents the 6 delocalized electrons. So there are 6 delocalized electrons. And as you know, 6 delocalized electrons equals 3 covalent bonds. But those 3 covalent bonds are spread over 6 carbon atoms. So really, if you want to think about benzene in the right way, you should think about it maybe like this, like partial double bond, partial double bond, partial double bond, partial double bond between all of the carbons like that, where the 6 electrons can whiz around there above and below the plane of the atoms. Side on, if I draw the hydrogen, carbon, 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 hydrogen, and draw like the hexagon side on, I want you to picture that really we should be talking about electrons whizzing around above and below. Above and below the plane of the board. So that you've got the atoms all in one plane and you've got these electrons above and below. Now the electrons are really important because when you have an electrophile, and as you know, electrophiles, like electrons, they're going to love this molecule, aren't they? Look at all those electrons whizzing around there. Electrophiles are going to really like that, and we'll see how benzene reacts in the future. This will be a key aspect. A key aspect will be that you will need to know what the structure is. You'll need to know then or you will learn, if you know what the structure is, why the reactions happen as they do. Because they're not, as you might expect, they're not addition reactions. They are something different, which we'll talk about later when we do the mechanism that's involved here. Okay, so I hope that's helped you get your mind around the structure of benzene. Now, if I was in school, we've got some polystyrene models which we've made where I could wave them around, but sadly, I'm not in school. When will those times come back when we can be with each other again? All right, lads, I'm going to stop the recording there. How do I stop the recording?